Hello everyone, my name is Isabelle. I'm a PhD student at the University of Neuchâtel, and I am here today to present you PipeTune, Pipeline Parallelism of Hyper and System Parameters Tuning for Deep Learning Clusters. This is a work I have done under the supervision of Professor Pascal Felber and Valerius Chiavoni, also from the University of Neuchâtel, and in collaboration with Nathaniel Morris from the Ohio State University, Professor Liu Chin from TU Delft, and Robert Berg from ABB Research. So let's start by considering a typical deep learning application where you have several labeled photos and you want to train a network which will be able to classify those photos. Although this is a straightforward problem, there are several questions you have to think about even before starting the training, such as how many layers to use, or even how many neurons each layer should have, how many epochs should your training consist of, and so on and so forth. All of these are called hyperparameters and are used to control the learning process. The most straightforward way to define those parameters is by actually fixing some values, letting your model train, and check if the achieved accuracy is sufficient. If this is not the case, then you can repeat this process with different values, which might increase or decrease your accuracy. But you can still keep on asking the question, what if I try yet another value for those hyperparameters? This process quickly becomes impractical, so that's why a common approach is to use hyperparameter auto-tuners. When using those tools, the user simply has to define the model and the data set, the set of hyperparameters and the range of values which they can take, the metric of interest, which in this case would typically be accuracy, and an optimization function, which in the case of accuracy would be to maximize it. Then all of this is given as input to one of the hyperparameter tuning tools that we have available, such as Amazon SageMaker, Google Vizier, Tune, or Optuna. And those tools are used as a black box, giving as output the final model together with the set of hyperparameters used to train it. Now the first question that we can ask is, what is the problem in the existing auto-tuning alternatives? First of all, the tuning duration grows exponentially with the number of parameters being tuned. Second, the user can only define one objective function, which typically is accuracy, and the tuning performance is therefore ignored. One way to mitigate this problem could be by using more powerful machines, but the more resources we have, the more expensive it gets, so this is not always the most feasible solution. The next question would then be, how can we improve this process? While thinking about this problem, the first observation we made was that hyperparameters not only impact accuracy, but also tuning duration and energy. To illustrate this, let's have a look at the scenario where we start with batch size 32 and compare the difference between accuracy, duration, and energy when varying the batch size to 64, 256, and 1024. In this specific example, we see that accuracy is indeed affected, but the impact on duration and energy is even more significant. The second observation we made was that there is no global optimal set of system parameters, but it actually depends on the chosen hyperparameters. Again, to illustrate this observation, let's have a look at this example, where we now focus on how duration differs from 2, 4, and 8 cores when compared to 1 core only. And we look at those values for batch size 64, 256, and 1024 again. The takeaway from this plot here is that varying the number of cores has a different impact depending on the batch size defined. Now we would like to leverage these two observations to propose a novel tuning approach. For that, let's start by having a look at how this tuning black box works in practice. First, a set of hyperparameter values are chosen based on the defined range, and the workload is trained with those values on what we call a training trial. As an output of a trial, we will have the trained model and the metric of interest corresponding to that trial. This process will repeat several times for different values, which will be chosen following a specific strategy depending on the optimization algorithm being used. For example, grid search will simply try all the possible values in the range. But there are also other algorithms such as random search or hyperband, which will apply techniques to reduce the search space. Independent of the algorithm being used, when all the trials are performed, the objective function is applied and the model of the winning trial will be outputted together with its hyperparameters. As we propose to include the system parameters in this process, the first modification is that the user now also defines the set of system parameters he's interested in tuning. And all the other changes will happen in the background, so they are invisible to the user. First of all, the training trial will trigger an asynchronous call to what we named a probing component. The probing will be responsible for tuning the system parameters for that specific trial. This is done by setting different system parameter values for each epoch and choosing those parameters which perform the best in the epoch level. They are then applied to be used on the remaining epochs of that trial. To further optimize this process, we also save those values to be used in the future by similar jobs. But considering that user privacy is an important aspect, instead of keeping user-sensitive information related to the workload, we save the optimal configurations together with a profile of a trial. To build this profile, we rely on higher performance counters to collect low-level system metrics. Finally, we add one last component named the ground truth, which consists of a similarity function based on the historical profiling data and implemented in this case using a k-means clustering algorithm. So when the trial starts, the profile of the first epoch is passed to the similarity function, and if the result is above a given threshold, then we can skip the probing component and instead rely on the historical data. The last difference is that as part of the final result, we also provide the optimized system parameters. Now, in order to evaluate our proposed approach, we have performed an evaluation using state-of-the-art workloads, which are listed here. As baseline, we use the Tune library, which considers hyperparameter tuning only with the objective of maximizing model accuracy. Regarding the environment, we consider a single node where PipeTune was implemented on top of Keras and TensorFlow, and a distributed setup which relies on BigDL running on top of Spark. In each of these environments, we consider two different scenarios. The first one is a single tenancy scenario where we show the results of running an independent unseen hyperparameter tuning job. And in the second scenario, we consider multi-tenancy, which shows the averaged response time. Let's then start by having a look at the evaluation results for scenario 1 in a single node environment. Regarding accuracy, we don't observe any gains, which is expected as this is not really the focus of our approach, but it is also important to mention that the performance does not degrade. For tuning duration, we observe that PipeTune performs considerably better than the baseline, and also that these gains are reflected on the tuning duration, as you can see on this plot here. Finally, the energy consumption is also improved as a reflect of the overall performance gains. Regarding scenario 2, in general lines, we could observe an overall gain on the average time when compared against the baseline in both environments. Now, to wrap it all up, we have presented PipeTune in our approach for DNN tuning jobs, which leverage the combination of hyper and system parameter tuning to achieve high model accuracy under low runtime and energy consumption. Our experimental evaluation performed under various scenarios and using different state-of-the-art workloads indicate promising results. PipeTune reduced the tuning time by up to 23%, speeds up the training time by up to 1.7 times, and lowers energy consumption up to 20%. In the paper, we also presented an intermediate solution, which we came up with before the final version of this approach, and this is also used as a baseline in the evaluation. So you're welcome to check the paper for more detailed evaluation. And then also, the source code has been made available, And you can find it in my Git repository under this address, so feel free to check it out. With this, I conclude my presentation and thank you for your attention.